Hi everyone, this is the fourth video on how to use genetic algorithms with Python. In the previous videos, we learned how to model a slab with columns in some random positions, specific with 4 columns. In the next video, we learned how to start the initial population and how to convert the chromosome data, which is in binary, back into decimal data. And then in the next video, we just learned how to get the fitness function, which in this case is the displacement in the z direction. We're going to find that maximum, and that's going to be our fitness. And obviously, we want to minimize that, but we're not coding that just yet. So for now, I'm just going to minimize this. I'm happy with that. And this, I'm going to send this down just in case if I need, but I'm going to comment because that's not what I'm going to work on now. So what we're going to work on today is we have the evaluation done, and now we're just going to do the selection, the reproduction, and the mutation. I would say we can do in one video, and then we're going to figure out how we can get the new generation going on. So as before, I'm just going to find those in another file, and then we can look through them. These are not complicated functions, despite sounding complicated. They're actually quite intuitive once we have a look at them. So I have here my tournament, that's for selection. I have my mutate, which is obviously for mutation. Then we have the new population, which is a bit chaotic. That's the one that does the babies. And I guess that's it. I think let's do those three, and then we'll have a look. So I'm going to copy this, and then I'm going to put it here. So I'm going to try to keep them in order. So initial population, then how to convert, calculate displacement, and then once we have our displacement, this is where we're going to start coding the next population. So the first thing we can look for is this tournament selection. So tournament is a very simple method of selection in genetic algorithms. So what we're going to do is we have the population that has been the one that just been calculated. Let's call it old for this sake. And then in this particular case, I allow for player's number to be a parameter. So a tournament is very simple. So the way this works is, well, I might not need a drawing for this. The way this works is if you have 2 players, the best player wins. It's that simple. If you have 3 players, the best player wins. If you have 4 players, the best player wins. If you only choose 2, and you choose 2 at random, so you take randomly from the population, you select 2 at random, and then the best one you're going to select for the babies step. If they're not the best one, then you don't do anything, which means they can actually get selected more times. And this is all done randomly. So one of the beauties in genetic algorithms is there's a lot of randomness. That's why you can never guarantee success every time you run it. But on the other hand, you guarantee a really decent success every time you run it because it's so random. It's impossible that you don't find the best specimens for a specific problem. That's why this is a very interesting method. So the first thing we do here is we have the WW, which is randomly selected from the population. So WW, it's just a number between 0 and the length. Okay, simple. Then the winner becomes that one. So immediately I say the one that is selected is the winner, and then I make the counter equal to 0. And then what I say is, okay, if the counter is less than player numbers minus 1, I'm going to go and bring a CC, which is another random number, and that's my challenger. Okay, so I'm going to run this as many times as the number of players minus 1. So I select a winner. The first one I pick is the winner, and then the challengers are the ones that are going to take the title from the winner, basically. So I run this as many times as necessary, depending on the players' numbers. If the player numbers are just 2, then I just run this once, and I check if the challenger beats the winner or not. Okay, I have a little code here. Remember to verify that the fitness is the last value. So I'm going to keep this here just in case something shows up in future videos. But this is very simple. So if the challenger, so we're going to compare here if the last value attached to the winner is less than the challenger, then we continue. Otherwise, the winner becomes the challenger and the winner becomes the challenger, or the other way around. The challenger becomes the winner. It's the other way around. When you think in coding and mathematics, is the other way around. And then we move on the counter. So it's a very simple function that the only thing that does is compares the fitnesses for different players, for different specimens, and then chooses the best one out of them. So the only thing that we might need to look is check later if we want to minimize or maximize the fitness. So the way I understand this, so if we go back into the previous video and what we did there, the displacement here is 24.18, and obviously I want to minimize this, so I want the displacement to be as small as possible. So if I go and I say, if the winner is less than the challenger, then we continue. So if means the challenger is less than the winner, then the challenger wins. So this is fine. I think the way this works, so I can put a note here, I think this is correct already. Okay. Now, in case, imagine that you want to maximize the displacements, or you want to maximize, I don't know, the profit or something else, right? Any other quantity you want to maximize, the only thing you have to do is change this to become greater, and then that's it. So that's it. So this is the selection using tournament. So it's a very simple selection. And then what the new population does, it runs the tournament to select the father and the mother. What the father and the mother will be is running the tournament function 2 times, right, to get the father and the mother, and then we're going to look into the rest in a little bit. So what this does, new population starts with an open list, with an empty list called new pop. The counter equals to select. So I'm not sure what this does. Okay, so this does elitism selection. Okay, so what basically this does is instead of selecting based on the tournament, the elitism is actually you just go and select the best of them. And now this is a very theoretical and philosophical discussion about why you want to have this here, but in very simple terms is you have to imagine that you're going to start with a very random list of specimens, okay? Some of them are going to be okay, some of them are going to be bad. But that doesn't mean that the bad ones have not interesting features that could be really, really good. So this is something that can happen, is you can have a specific element of a population that, when compared to the others, is not the best, but still has features that would be important to keep. Okay? And what the tournament does, it gives a chance to this one that is not the best to even survive by competing with ones that are worse. So what the elitism does is to guarantee that at least the best one in total stays in the population. That's the gist of this. But anyway, so counter equals select, and then population size is this. So that sounds like a useless thing to do. So let me just fix this. So with the years, you kind of get better at coding. So this is an easy win. So then I sort the old population. Okay, and the elitism what does is selects a few, in this case, counting this based on this select variable, selects a few of them and puts them straight into the new population. Okay, so this doesn't even go into tournament. It's like, are you the best in this population? Okay, then you survive. The end. So I'm happy with that. Then the tournament is like we discussed. So if the counter is less than the old population, we want we want the new population to be the same size as the old one. So if you start with 100 specimens, you want at the end to have 100 specimens as well. So what this does is finds a father and finds a mother by using this tournament function that we discussed already. And then from the child 1 and child 2 are just empty lists for now. And now this does the crossover of genes. So if a random number between 0 and 1 is less or equal than 0.7, what this basically means is this has 70% chances of occurring. So 70% of the times, the father and the mother will make babies. And that's what basically this does, is if this random number between 0 and 1 is less than 0.7, then this is successful. So then you're going to get child 1 and child 2 to be a choice between the father and the mother. So the way this basically works is, I might need a drawing for this. Imagine that we have a certain father and a certain mother. So this list of numbers is the father, let's say, and then this list of numbers is the mother. Okay? What that will basically do is to say, okay, if I have to make a baby that it takes the genetics of both the father and the mother, the baby should definitely have a 0 here, because both the mother and the father have a 0 there. And here should definitely have a 1. Okay? And this is valid for here, here, and here, because both the father and the mother have the same genes, so that's the ones you want to keep. And now, every time there is a decision to be made between you want to take the father or the mother, you do it randomly. So you either get a 1 or you get a 0. Okay? And this will be your first child. Okay? Your second child is the same logic. So these ones will definitely be the same in your second child. Takes again randomly a choice between the gene of the mother and the gene of the father. So that's what this function does. So random choice between the father at position I and the mother at position I. But that's it. If this is not active, so if this random number is not less than 0.7, so that's 30% of chance, the child 1 and child 2 just become the father and the mother. So the father and the mother go straight into the new population. And again, this is something you want to do. You don't want to mix the genes too much. You don't want to mix too little. This 70% chance of occurring, and this is a parameter that you can change, depends on the problem, but allows you to control the speed of converging into your optimal specimen. Brilliant. Then obviously the counter goes counter plus 2. So this basically means I just added 2 people into the population. And while this is, if this is not true, then this will run again until I get to the desired length. Now, the last thing is the mutation of the child. After you run your selection, we have mutation. So mutation is very simple. It's just changing the one of the chromosomes at random. So if we go here to mutation and then we'll go back up, if this number is less than a probability, so again, this has a probability of happening. Usually this is very low. We want this to be like 10%. So what I'm going to do, actually, I'm going to make a comment on this for now, and then I can talk to you about this towards the end of the videos, because that's a little bit more advanced. So I'm going to comment these two, and I want probability of mutation just to be 10%. Okay, so like this. So if the probability is 10%, what this does is, if this is active, a random gene is selected, and then if the random gene is a 0, becomes a 1, or if it's a 1, it becomes a 0. So it's very simple. You just basically find somewhere in the chromosome, randomly, you select a gene and you flip it. And that's what the mutation does. So that's basically it. So after you do your selection, the child, which by the way, the child here can be the father and the mother, there's 30% chance of that. They get mutated 10% of the times, okay? And that's it. Then you append the child to the new population. And that's it. So what this basically does is tournament selects the best, basically. Mutation allows you to have a little bit of craziness in your genetic pool. And again, this has to do with how genetic algorithms work. You don't want to converge too fast, because imagine that in your initial population you get a really good specimen. It's not the best specimen, but a really good one. That one basically can converge the entire population to their own genetic code and don't let the other ones have a fighting chance to spread their genes. And then you might end up converging into a solution that is not the best. It's okay, but not the best. So what these mutations do, what these probabilities do, is basically guarantee that there's a sentence you hear a lot in genetic algorithms: you explore and you exploit. So you don't want to explore too much, because then you just end up studying a lot of specimens. You don't want to exploit too much, because then you might miss some genetics combinations that would be interesting. Okay, and it's this balance that makes genetic algorithms quite an interesting topic for research. So that's it. So what we learned to do today is mutate, tournament, and how to calculate a new population. Now, what we have in mind for the next video, this was a smaller one, but what we have in mind for next video is basically running the cycle. So now that we have all the ingredients to do our cycle, what I want is to start running this cycle. So you have the initial population, then it plugs in Abaqus, then selects, then gets the new population, then it repeats for a number of generations. So thank you for watching, and have a nice day.